I want to do a few examples using the ideal gas equation. The ideal gas equation is used when you're given one set of conditions for a particular gas sample, as opposed to one set of conditions and then something changes and you have another set. If you look at this problem, the question says how many moles of a gas would occupy a volume of 15 liters at a pressure of 3.2 atmospheres and a temperature of 295 Kelvin. Well, that's just one set of numbers. We're not changing anything. So this works really well with the ideal gas equation. So the ideal gas equation is pressure times volume equals N times R times T. R, we know, is the ideal gas constant, which is 0.0821, and the units have to be atmosphere liters per mole Kelvin. So all of those other four variables have to be in units of atmospheres, liters, moles, and kelvins. Pressure here looks like it's 3.2 atmospheres. Our volume is 15 liters. That equals the moles, which I don't know, times 0.0821 atmosphere liters per mole Kelvin times my temperature of 295 Kelvin. So if we cancel out units, Kelvin cancel out, liters are on both sides, they're gone, atmospheres, both sides, they're gone. To get moles by themselves, I just need to divide both sides by 0.0821, and now that's per mole, and 295. So to find my moles, I'm going to take my 3.2 times 15 divided by 0.0821 divided by 295, and that would be, with two significant digits, 2.0 moles of the gas. All the units canceled out except for moles. When you have divide by 1 over moles, you get moles for the unit, and we're good. If you look at this next one, same idea. I am given, question is, what is the volume? I'm given moles, I'm given a pressure, and I'm given a temperature. Well, there's only one set of conditions, which means it's the ideal gas equation. So P times V equals N times R times T. In this case, my pressure is 750 millimeters. Well, I know it has to be in atmospheres. So the first thing I have to do is change my millimeters of mercury into atmospheres. I know there's 760 millimeters for every 1 atmosphere. So put the 760 on the bottom. The millimeters of mercury cancel out. And when you take 750 divided by 760, you get 0.9868. 0.9868 atmospheres. So that will go right here for the pressure, 0.9868 atmospheres, times the volume, which I don't know. That equals the moles, which is 4.5, times 0.0821 atmosphere liters per mole Kelvin, times my temperature, which is in Kelvin, 325. Notice my moles cancel out, my Kelvin cancels out, my atmospheres cancel out, and I'm left with liters for units. So when I take my 4.5 times 0.0821 times 325 divided by 0.9868 with, it looks like, two significant digits again, my volume is simply 120 liters. In this case, both sides had to be divided by 0.9868 atmospheres, so they canceled out to give me this answer. And one more to try. How many grams of oxygen are required? Well, in this case, what am I given? I'm given grams, or at least I want to find that. I'm given a pressure of 0.98. I'm given a volume of 21 liters and a temperature of 25 Celsius. Excuse me. So I'm only given one set of numbers, which means I need to use the ideal gas equation. P times V equals N times R times T. Nowhere in this equation is there a place to find grams. However, we know that moles are related to grams via the molar mass. So if we plug in what we're given here, my pressure is 0.98 atmospheres. The volume is 21 liters. I don't know what the moles are. I know R is 0.0821 atmosphere liters per mole Kelvin. Temperature, in order to cancel out these units of Kelvin, needs to be in Kelvin. So to find my Kelvin temperature, that's Celsius plus 273. So 25 plus 273 gives me a Kelvin temperature of 298. That goes right over here, 298 K. In order to find N, I'm going to divide both sides by 0.0821 atmosphere liters per mole Kelvin and 298 Kelvin. So divide this by 0.0821 atmosphere liters per mole Kelvin. They're gone. And the 298 Kelvin, that's gone. I'm left with N equaling, notice my atmospheres cancel out, my liters cancel out, Kelvin cancels out. We have 1 over moles on the bottom. You get moles for your units. And let's take 0.98 times 21 divided by 0.0821 and divide that again by 298. I would have 0.84117 moles of oxygen. But the question doesn't ask for moles, it asks for grams. But we all know that we can change moles into grams very simply by looking at the periodic table. The molar mass of oxygen, 1 mole of O2, is 32 grams. So when you take your number of moles times 32 grams per mole, we get, with 2 significant digits, 27 grams of O2. Again, one set of numbers implies you will probably use the ideal gas equation.